Hello everyone and welcome back to tutorial 10 of MIE100, the dynamics course at the University of Toronto. Today our tutorial is going to be about the dynamics of rigid bodies, plane kinetics of rigid bodies, and specifically about work and energy. That's going to be the new material that we're going to be covering. We're going to be doing 3 problems, and through those 3 problems, I'm hoping that you would be able to solve work and energy related dynamics of rigid bodies problems. And as usual, if you have any questions, leave your comments in the comment section below. Okay, so starting with our first question, we've got a truck that carries a 1,500 millimeter diameter spool of cable with a mass of 0.75 kilograms per meter of length. There are 150 turns on the full spool, and the empty spool has a mass of 140 kilograms with a radius of gyration of 530 millimeters. The truck alone has a mass of 2,030 kilograms with a mass center at G. So if the truck starts from rest with an initial acceleration of 0.2 multiplied by the acceleration of gravity, determine A, the tension T in the cable where it attaches to the wall, and B, the normal reaction under each pair of wheels. Neglect the rotational inertia of the truck wheels. Okay, so that's a lot of information to take in and digest. So, as usual, we'll start with our knowns. We know that the diameter of the cable is 1,500 millimeters or 1.5 meters. We also know that the mass of the cable per length is 0.75 kilograms per meter. We know that the number of turns is 150. We know that the mass of the empty spool is 140 kilograms. The radius of gyration of the spool is 530 millimeters or 0.53 meters. And we know that the mass of the truck is 2,030 kilograms. And our initial acceleration is 0.2 multiplied by the acceleration of gravity, which gives us 1.962 meters per second squared. Okay, so for our first question A, we want to determine the tension T. So for that, we're going to draw a free body diagram first, as always. And I'm going to draw a free body diagram of this spooling cable. So we've got the tension in the cable here. This is the free body diagram of the cable. So we've got the tension, we've got the mass, the weight of the cable, and we also know that the truck is moving forward, and and the spool is attached to the center, so we've got a reaction force going this way. And we also have a reaction force going this way against the weight. So with that information, we're going to take our angular motion relations. And we're going to try to find our angular acceleration. So we know that the tangential acceleration is equal to alpha multiplied by r. And since we already have the tangential acceleration over here, which is 1.962, we can easily find the angular acceleration. It's just going to be the diameter over 2 to get 2.616 radians per second squared. Now, we want to find our plane motion equations. So we want to find the sum of moments around O. And that's equal to rotational inertia multiplied by the angular acceleration. So, this is going to be some new material. For the rotational inertia, we're going to have a new equation called the fixed axis rotation. So for a fixed axis rotation, when you have the radius of gyration given, such as in this question, the rotational inertia automatically becomes I is equal to rotational inertia k squared multiplied by m. This is the radius of gyration. So since we have that, we can now calculate our rotational inertia for the spool easily because we've got the radius of gyration. So it's going to be the mass of the spool multiplied by the radius of gyration squared. That's for the spool. Now for the cable, it's going to be a little bit more complicated than that. We want the rotational inertia of a hoop about a symmetry axis. So the rotational inertia of a hoop about a symmetrical axis is equal to I is equal to mr squared. Pretty simple, right? But to find the mass, we're going to have to find the length because we've got the mass per length. So it's going to be mc per lc. And to find the length, it's going to be the number of turns, nc, multiplied by pi dc for the circumference. And then finally, we're just going to multiply that by the radius, which is dc over 2 squared. And that's for the cable. Now that we've got our equation ready, we can plug in our known values. To get the rotational inertia about center O to be equal to 337.5 kilograms meters squared. Now, we want to find the sum of moments about O, which is equal to force times distance, or in this case, for us, it's T multiplied by D, or D over 2. So we're going to take the clockwise to be positive, and That will give us T multiplied by 1.5 over 2 is equal to this rotational inertia, which we just found, 337.5, multiplied by the angular acceleration, which we also found earlier, which is 2.616, to give us a value for the tension T, which is 1,177 newtons. Okay, now for part B, it's asking for the normal force A and normal force B that's acting on the wheels of the truck. Now, as usual, we're going to draw our free body diagram of the truck. Here's our little truck with the wheels, NA acting this way and NB acting this way. There's a frictional force acting that way, or no. Frictional force will be acting this way. That's just assumed. We've got our OY and our reaction force R. Center G, and the total mass of the truck. And it's moving forward with this acceleration. So, knowing that the rotational inertia of the wheels is 0, we can first try to find our OY and R before we start with our analysis for the normal forces of NA and NB. So, going back to our free body diagram over here, we can easily find the reaction forces of OY and R because we've already found the tension force T. So all we have to do really is our plane motion equations, or Newton's second law. Sum of forces is equal to ma. And in the positive x direction, Fx, based on this free body diagram, is R minus T is equal to ma. So R minus T is equal to ma. Knowing the value for tension, we're going to plug that in. And then for M1, it's just the mass of the spool and the cable. So it's going to be 140 plus the circumference multiplied by the number of turns and the mass per length. All of that multiplied by the acceleration, which we found to be 1.962, to give us a value for R to be 2,492 newtons. We're going to do the same thing, but in the Y. So sum of forces in the Y, based on this free body diagram, is going to be OY minus M1G is going to be 0 because acceleration is 0 in the y direction. So y is just going to be equal to the mass, again, of the spool and cable, which is 140 plus pi times 1.5 times 150 times 0.75 multiplied by 9.81 to give us a value of OY, which is 6,574 newtons. Now that we've gotten our reaction forces R and OY out of the way, we can start finding the sum of moments around A in the free body diagram of the truck. Now we can take a look at the free body diagram of the actual truck. So the sum of moments about A is just going to be equal to the sum of forces multiplied by distance, which is equal to MAD. So let's take the clockwise direction to be positive. Sum of forces, sum of moments around A is going to be equal to OY multiplied by 0.75 plus MTG multiplied by 1.8. Now these distances are all over here. So this is the 1.8 and this is a 0.75. So just refer back to the diagram to follow through. So it's going to be minus R multiplied by 1.65 plus 1.5 over 2 minus NB 1.8 times 2, because B is twice that length away from A, and all of that is going to be equal to M2 AG multiplied by 1.05. That's the mass of the truck multiplied by the acceleration and total distance from A. Okay. So now that we've got that equation, now all we have to do is plug in our known values. To get a final answer for the reaction on the normal reaction on B to be 8,504 newtons. Now, finally, after we found the normal reaction force on B, we can easily find an A by doing the sum of forces in the y direction. So sum of forces in the y is going to be equal to 0 because it doesn't accelerate in the y. Sum of forces is going to be NA plus NB plus, minus M2G minus OY is going to be equal to 0. And once we plug in our known values, we can get a final value for the normal force at A to be 17,984 newtons. That's the final answer for question 1. Now for problem number 2, it's going to be a little bit trickier, but bear with me. We've got a 25 millimeter thick uniform steel plate being pulled very slowly into position by the cable connected to a winch. If the cable breaks at the instant represented, determine the magnitude of the force under each roller and the vector acceleration ag of the center of mass. Neglect friction and the mass of the rollers and consider the rollers small. Evaluate your results for A is equal to 3 meters, B is 6 meters, and R is 6 meters. Note that arc BC is of radius R, the same as arc BD. Okay, so that's, again, a lot to take in. So let's just write our known values. So we know that the thickness of the plate is 25 millimeters, or 0.025 meters. We know that A is 3 meters, B is 6 meters, and R is 6 meters. We know that it's made out of steel, and that RBC is equal to RBD. And we want to find the reaction force at A and at B. We want to find the vector acceleration at center G. Okay, so we're going to start, as always, with a free body diagram. So this is going to be a detailed free body diagram, and it might be a little bit messy, but bear with me here. So this is approximately what the path looks like. We've got a plate here. This is point A, this is point B, this is point C. This is going to be our point G, and our weight pointing down. This is our y and x coordinates, and the anti-clockwise rotation is going to be positive. This is our length A and length B. This is our point D. And let's call this angle over here theta. This is going to be the acceleration at A, and this will be the acceleration at B. So with the angle phi over here, this must mean that the reaction force at A will have an angle of phi over here as well. It will also have reaction force at B here. This is going to be 30 degrees, and this is also going to be 30 degrees, which means that this angle over here is also 30 degrees. However, this angle over here must be phi, and this angle over here is also phi. This angle over here is also phi, and hopefully I've labeled all the important angles. So now let's take a closer look after we've drawn the very detailed free body diagram. We've got our forces, our reaction forces on A and B, our accelerations at A and B, the weight at G, and a bunch of angles. Now, the most important thing to get out of the way is to actually find the angle phi. And although this might look hard to begin with, but if we take a closer look at our path from A to C, this is what our path looks like from A, C to B. And our steel block kind of is at an angle from A to B. And we know that this angle over here is phi. So if we want to find that angle, we're going to need to write an appropriate equation. So the distance between A and B vertically is B sine phi. And because the angle over here is 30 degrees, the distance between B and that point over here is r cosine theta, because the radius BC is r. So that means that this is r, and this is also r, right? So knowing that, we can say that B sine phi plus r cosine 30 is equal to r, because the distance from this point to C is also r. So if we rearrange that equation, and plug in our known values, we can get a value for phi to be 7.7 degrees. Now that we've gotten that out of the way, we need to find the value for the mass. Now, we're not given the value for the mass of the block. However, we do know the volume, and we can potentially find the density from the material. So the volume of the block is A multiplied by B multiplied by the thickness, and the density is going to be theta. So if we try to find the density of steel online, we get a value of 7,830 kilograms per meters cubed, which means that after plugging in our equations, can get a value for the mass to be 3,524 kilograms. Now, after we found the mass, we can now start writing our kinetics and kinematics equations. Now, for this problem, we're going to have 7 unknowns and 7 equations. So, based on the free body diagram, let's start with the easiest. So let's start with our sum of forces. Our sum of forces in the x is going to be equal to MA GX, which is MB sine 30 is equal to MA GX. Now, what about our sum of forces in the y? Our sum of forces in the y is going to be equal to MAGY, which is equal to NA plus NB cosine 30 minus MG, which will give us MAGY. So that's our first equation, and that's our second equation. Now we're going to do sum of moments around G. Our sum of moments around G is going to be equal to IG multiplied by alpha, the angular acceleration. And to find the rotational inertia about G, we're going to treat it as a flat plate rotating around the z-axis. So for that, it's going to be equal to 1 over 12 multiplied by m multiplied by a squared plus b squared. This equation over here is for a flat plate rotating about the z-axis. Now we can finally plug in our sum of moments equation, so minus NA multiplied by b over 2 cosine phi plus NA multiplied by a over 2 sine phi plus NB multiplied by b over 2 cosine. Okay, let me write that on the next line. Plus NB multiplied by b over 2 cosine 30 minus phi. This is because over here you can see that this angle over here that we need to find is equal to 30 minus phi. So we're going to do the same thing in the x direction, in the y direction. So minus NB multiplied by a over 2 sine 30 minus phi. And all of that is going to be equal to 1 over 12 MA squared plus b squared. This equation over here is our third equation. Now that we are done with our kinetic equations, we're going to go about our kinematic equations. So for our kinematics equations, we're going to start off with some relative acceleration equations. So we know that AG is going to be equal to the acceleration of A plus the acceleration of G with respect to A. And knowing our angular motion relations, that's going to translate to acceleration of G is going to be equal to acceleration of A plus angular acceleration cross product or GA plus omega squared RGA. However, this part is equal to 0 because it's at the instant when the cable breaks. So omega is equal to 0. Now to find the relative distance of G with respect to A, it's going to be equal to B over 2 cosine phi minus A over 2 sine phi in the I direction plus minus B over 2 sine phi minus A over 2 cosine phi in the J direction. And once we plug our values in, we can get a value for the distance between G and A to be equal to 2.77 I plus 1.88 J. Now if we plug that back in to our equation over here, get AG is equal to AAI plus alpha in the K direction, cross product 2.77 I plus 1.88 J, which means that in the I direction, we've got AGX, so AG in the X direction is going to be equal to AA, which is only in the I direction, minus 1.888 alpha. So that's going to be our fourth equation. And in the J direction, we've got AGY is equal to 2.77 alpha. This is our fifth equation. And now we're going to do the same thing, but with the acceleration at B. So the acceleration at B is going to be equal to the acceleration at A plus alpha multiplied by the respective distance of A with respect to A with respect to B. So again, we're going to try to find the distance of A with respect to B, which is equal to B cosine phi I minus B sine phi J. Once we plug those into the equation, you can get the 5.95 I minus 0.804 J. And if you plug that in back to our equation over here, you can get AB is equal to AA in the I direction plus alpha in the K direction, cross product 5.95 I minus 0.804 J. That means that in the I direction, we've got AB cosine theta, or cosine 30, because over here, if you remember, our AB is pointing this way. So to get our axes straight, you need to make it cosine and sine 30. This over here, this angle over here actually isn't phi. This angle over here is 30 degrees. So in the I direction, AB cosine 30 becomes equal to the acceleration of A plus 0.804 alpha. In the J direction, AB sine 30. In the negative direction, so it's negative, is going to be equal to 5.95 alpha. So this is our 6th equation, and this is our 7th equation. Now that we've got 7 equations and 7 unknowns, which are NA, NB, AB, AG, alpha. Sorry, this is AA, alpha, AGX, and AGY. Once those equations are solved simultaneously, we can get a value for the reaction at A to be equal to 15.93 kilonewtons. And for B, it's going to be 18.33 kilonewtons. For the acceleration at A, it's going to be 3.13 meters per second squared. The acceleration at B is going to be 3.36 meters per second squared. The angular acceleration is going to be negative 0.82 radians per second squared. So it's going to be turning clockwise. AGX is going to be 2.6 meters per second squared. And AGY is going to be negative 0.82 meters per second squared. Which means that our vector acceleration of center of gravity, G, is going to be equal to 2.6I minus 0.782J meters per second squared. That's the end for our question 2. Now for our final problem, number 3, we have a uniform disk with a mass of 24 kilograms and a radius of 0.3 meters, initially at rest. It is then acted upon by a constant 100 Newton force as shown and rolls without slipping. We have to determine the velocity of its center of mass after it has moved 1.8 meters and the friction force required to prevent slipping. So for this question, our known values are the mass, which is 24 kilograms, the radius, which is 0.3 meters, the force, which is 100 newtons, and we know that it rolls without slipping. So for part A, we want to know the velocity of the center of gravity G. After a change in distance of 1.8 meters. So as usual, we're going to start with a free body diagram. This is our disk. This is our G, and our force P, our weight pointing down. At this point, we've got our friction force and our normal force. This point over here is going to be our instantaneous center of rotation. These are our y and x axes. So for this problem, we're going to use our work energy equations, which is T1 plus U12 work is equal to T2. However, we know that T1 is 0 because it starts from rest, so V0 is 0. And now we're going to get into some new material. Which is the equation for kinetic energy of a rigid body in plane motion. So we know that T is equal to half mv squared, but it's also equal to half IC omega squared. So in our case, T2 is equal to half I ICR, instantaneous center of rotation, multiplied by the angular velocity squared. Now, what's the rotational inertia of around the instantaneous center of rotation? We've got the rotational inertia of a disk, which is equal to half mr squared. So it's just the IO of a disk plus mr squared, because we're translating that to the ICR. So translation to the center of rotation instead of the center G. So now that we've got all of our known values, we can plug them in to get half multiplied by 24 multiplied by 0.3 squared plus 24, and the distance between G and the center of rotation is also 0.3 squared, which is going to give us a rotational inertia of 3.24 kilograms meters squared. Now for the work done from 1 to 2, that's going to be equal to the force multiplied by the change in distance, which is given to be 100 multiplied by 1.8. Therefore, the work done is going to be equal to 180 Newton meters. Now, if you plug those in to this equation, we can calculate our rotation, our angular velocity. Get 180 is equal to half 3.24 multiplied by omega squared to get the angular velocity equal to 10.541 radians per second. Since there is no slipping, equation for velocity at g is going to be equal to omega multiplied by r. Thankfully, we have those. So that's going to be equal to 10.54 multiplied by 0.3 to give us velocity of the center of mass g is equal to 3.162 meters per second. So now that we've done with part A, we can start looking at part B, which is asking for the friction force to prevent slipping. Now, if we take a look at our free body diagram again, if we use our kinetic equations to find the sum of forces at x and our kinematic equations, we can simply find our frictional force. And this is by first doing our sum of forces in x, which is equal to magx. So our sum of forces is going to be equal to P minus the frictional force, which is equal to magx. And then if we recall our kinematic equations, if we recall this equation, which is Vg squared is equal to V naught squared plus 2 agx delta x, we know that V naught is 0. So if you plug in our known values, it's just going to be equal to 3.162 squared is equal to 2agx multiplied by 1.8 to give us a value for the acceleration of center of gravity and the direction x to be equal to 2.78 meters per second squared. And if we plug that in back here, we get 100 minus the frictional force is equal to 24 multiplied by 2.78 to give us a final value for the frictional force, which is 33.3 newtons. And that's the final answer. So that was the end of our tutorial. Thank you so much for listening. If you have any questions, email me at noor.doidar@miami-utoronto.ca or leave your questions in the comments below. And as always, see you next week.